This is the fourth in our series of talks about engineering economics. In this case, we're going to talk about the mechanics of calculating present value. So these are present value of future expenses that we might occur, or actually future benefits or future revenue. We already talked about the time value of money and why it is that we would be interested in doing this. So we're going to look at three cases. The first is a one-year benefit or cost. We're going to look at a uniform series. We've referred to this elsewhere as annual expenditures, where you have the same amount spent or revenue coming in or benefits coming in year after year. And the last we're going to be looking at are the gradients, which is basically an increase over time on an arithmetic progression from one year to the next. We already introduced these concepts when we were talking about cash flow diagrams. Okay, so it's not really that complicated of a concept, but imagine that here we have one cash flow diagram with a future benefit of $100,000 that occurs basically in year 3. What we're trying to do is what is the present value of that $100,000 in year 3. So we're going to create a second cash flow diagram essentially where the equivalent present value cost or is going to be revenue or benefit is going to be incurred in year 0. And what we do is we're going to calculate a factor, and there will be other factors like this for annual or gradient series. But in this case, we call this the P over F. So it's essentially the present value divided by the future value. So you can imagine if you multiply this by future value, we end up with the present value. And you can see it has two subscripts, one R for the interest rate, or the discount rate they're going to be used in doing this calculation. That value is actually not an easy thing to come by. Typically, your company or organization you might be working with would tell you we're going to use a specific interest rate, and there are a number of reasons why or how you would come up with that number. And the last N is essentially the number of years into the future that future benefit or cost is being taken on. And so here's the factor. P over F is going to be equal to 1 over 1 plus R raised to a power of N. And so you could code this into Excel, for example. And there are also charts, and I'm going to show you in a minute. There are tabulated charts. Before we had spreadsheets and computers, frequently people use these charts, and they still can be very useful even now. So here's an example. The P over F at a 4% interest rate or discount rate, 3 years in the future, equals 0.890. So we're going to multiply that by our $1,000 future benefit, and we're going to say the present value is 890. So this future 1,000 is equivalent to a present value of $890. We can also look at it further into the future. So we said in year 3, we have a P over F of 8.89. 10 years in the future, we're going to have 0.675. So you can see it's getting smaller. And 30 years in the future, it's 0.308. So a present value of $1,000 30 years in the future is only $300. So it kind of, what you're really getting at is that we probably don't want to spend more than $308 for a future benefit that would amount to a value of $1,000 30 years hence. That's essentially the implications of what we're looking at. And we can look at this on a chart. So in this case, we're looking at the present value of $1,000 at future periods, so 10 years in the future, 20, 30, 40, 50 years. As you can see, the value of that $1,000, the present value of the $1,000 gets smaller and smaller the farther out we get. So when you get out to, say, 40 years, it's only about $200. So you're really only, you can see why the engineering economics would tend to favor projects that have benefits incurred sooner, maybe 5 or 10 years, because those are going to be considered to have maybe 3 or 4 times the value of a benefit, that same intrinsic value benefit that's incurred in a period of 40 years from today. All right, we can do the same thing for a uniform series or annual series. So let's say we have a 100K uniform series. In other words, we have 100K spent every year, or excuse me, taken in each year from years 1 through 6. Remember, we're using that end of year convention. So 1 here is basically the end of year 1. And we want to know what is the present value, equivalent present value of this annual series. And there is a function that we can use. Well, it's not actually that hard to find these, but we can come up with a P over A factor. So in other words, you multiply the annual expense, in this case was 100K, times P over A, you're going to end up with the present value of that. And here is essentially the function. And again, R is the discount rate and N is the power. And so in this case, when we look at our 6-year 100K annual expenditures at an interest rate or discount rate of 4%, we end up with P over A of 5.24. And essentially that has a present value of 524,000. And if you add up the values, you see 1, 2, 3, 4, 5, 6 times 100, it's 600,000, but you're discounting, particularly the further out you go, the more you're discounting. So you end up with a present value of 524,000. Okay. Now the other type of series that we talked about. So we looked at a single expense or benefit, an annual or uniform series, and we can also look at a gradient. So in this case, remember the gradient starts out at 0 and goes up by an even increment. So in this case, we're looking at increment of 20K per year for essentially going from year 1 through year 6. So we're looking for the present equivalent value of this 20K gradient series. So you might not be surprised to see there is a P over G factor. So in this case, we'd multiply P over G times 20K to come up with the present value. The function is a little more complicated. When you get to, if you're coding this in Excel, it takes a little bit more effort. But it's not all that difficult to do. So you have P over G for an interest rate of R and for a duration of N years. And in this case, P over G would be equal to 12.5. So the present value is about 250K of this 20K gradient series going from years 1 through 6. And if you add the numbers, see, I was just doing that in my head, 100, 180, 240, 280, 300. So in this case, we have a $300,000 just added together, but it actually only has a present value of 250,000. All right, so I did say I've been showing you the functions to calculate these things, but there are lookup tables. Frequently, they'll have them in textbooks. They're actually not they're not as much around as they used to be. Many of the textbooks will have a set of tables that will look like this. And what you see here is each page will have for a particular interest rate. So on the page we're looking at, you see up here in the left-hand corner, it says 5%. So we're looking at this whole page will be for 5%. And if we look here, see this is a present worth factor, find P given F. So here's our P over F factor. So right here, we'd have P over F, because this is in year 10, we'd have a P over F of 0.6139 for an interest rate of 5 years. Okay, we also have, in this case, P over A. It's actually covered here, but that would be this column here. And then the last column on the right in this case is P over G. You can see that over here. And so if you can find the P over G value for any number of years gradient. All right, so this is a lot, and in this case, you can get to this particular table. This is online using this link. All right, so the next thing we're going to look at is, so now we know how to calculate present value for any particular expenditure or expenditure series. So now we're going to look at calculating the net present worth of a project that you might be thinking of taking on. That'll be in our next lecture.